All right, everybody, welcome to Math with Grace. Today we're going to be working on Relations and Functions, book 1204, lessons 4 through 6. Lesson 4 begins on page 13, and it's entitled Other Graphs. Super clear. Graphing the functions of tangent, cotangent, secant, and cosecant, and deriving properties of these graphs. So the tangent function y equals the tangent of x is a set of ordered pair real numbers. Again, we're dealing with real numbers. And they got it set up here and then have put in the values, right? A lot of the stuff we solved for in the other sections, or we can easily figure out for this section. But when graphing it, if we look here, the graph definitely has its own flair. And that comes in with these undefineds, okay? Now I marked the 0 point, right, on my thing. For whatever reason, they like to cut it out. And the 0 point is right here at 0, right? Here's our 0, 0. So here's our 0, 0. So even though the numbers start here and they only go positive, they did graph some of the negatives. Obviously, it would have continued with this downward angle looking like this, and so on and so forth, forever and ever, amen, right? With a break every time we hit this pi over 2, okay, which is right here, pi over 2, or any multiple of pi over 2 is undefined, is where we get this dotted line, okay? Here it is again at 3 pi over 2. Okay, we have another undefined area. And over here at negative pi over 2, okay? And it tells us here that extending the domain to negative 2 pi is less than or equal to x, which is less than or equal to 2 pi, results in the following version. Let's turn the page. So on page 14 here, it's a slightly larger version. Remember, this is our tangent, okay? Really not any different than the one that was on the page before, except it's just got a little bit of an expanded. It says, since x is any real number, the graph of the tangent of x continues both left and right indefinitely. Like I said, it goes on and on forever, amen. And obviously with these breaks here, okay? So let's do some of these problems. So question number 1 here is, at what interval does this tangent graph start repeating itself? And if you look here at this one in the middle, because here's our 0, right? It goes from negative pi over 2 to pi over 2, which is an interval of 1 revolution, right? It's basically 1. Yeah, then we go from pi over 2 to 3 pi over 2, which is basically 1 times pi over 2, right? So the interval that it repeats itself here is just pi. It's just 1/2 of the circle, or 1 point, right? Because remember, a full circle is 2 pi, so this is just half of the circle. What are the values of the domain of the tangent of x that are undefined? Well, if we look here, it's at negative 3 pi over 2, comma, and it goes on and on. So we could put our dot, dot, dot here with our squiggly line, and then it's at negative pi over 2, and it's at pi over 2, and it's at 3 pi over 2, and dot, 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 because remember, it goes on and on in both directions each way. Then the next question is 4.3. What is the range? Okay, what is the range of the tangent of x? Well, the range, remember, is all real numbers. So that's our answer. All real numbers. And then they want us to do some graphing. Now, what I didn't notice last week when I made the video for lessons 1 through 3 is this little note here at the bottom of the page. And it says that graph paper for these exercises is included in the back of this unit. That is pretty helpful. So we are going to move over to there to graph the tangent of these points. All right, so I flipped over here to page 34, and let's work through these problems. So I'm just going to write it right up here at the top. Problem 4.4 is y equals the tangent of x, comma, negative 2 pi is less than or equal to x, which is less than or equal to pi over 2. Okay, that's what they're asking me to graph. They've got the dotted lines in here for my 1 and my negative 1, making this my 0. Okay, pretty set up for us. It's pretty nice. So the first thing I'm going to do is grab my ruler here, and I'm going to mark off my breaking points, the undefined areas. And for this one, I need to go from 2 pi, which is way over here. Oops. I don't like random. Okay, so here's my 2 pi. I'm going to kind of just put a heavier check mark there. And I need to go to pi over 2. Pi over 2 is, and these aren't marked really correctly, but pi over 2 is basically right here. Okay, so let's see, where are our breaking points? Well, the first breaking point here is at negative 3 pi over 2. And these are so tiny. It's right about here, negative 3 pi over 2. This is why I guess necessarily don't like using this chart, because some things don't fall on a solid line. Where if we made our own chart, it could, right? The next breaking point is at negative pi over 2, which is here. So if you still want to use your own graph paper, because you can make these things on a solid line instead of these half points, by all means, I'm not going to stop you. The next breaking point, though, is at positive pi over 2, and that's actually where we are going to be ending, so I don't need to go any farther than that right now for this graph. So those are the undefined areas that we have to deal with when graphing this section, right? And then if you just study the chart that they gave us, the graph and the little number chart, we just have to put in what we know, right? We know that when we're graphing the tangent based on what they showed us on those other pages, that when it's at negative 2 pi, it's actually right there at the 0 point. So we can just make that a nice big dot. And since we're on this side, we know that it's going to go up to the 1, and it hits that 1 at negative 7 pi over 4. All the stuff in between there, I don't really care that much about. So we can connect these dots like this and draw an arrow, okay? Now, the next section, the first point is going to be the negative 1 at 5 pi over 4. It crosses the 0 line at negative pi, and it crosses the 1 line at 3 pi over 4, okay? So I'm just going to start at the 0 point, and I'm going to go like that and draw my arrow up and come back to the 0 point and then draw my arrow down. Okay, perfect. The next section, we cross our negative 1 at negative pi over 4. We cross the 0 at 0, which they never mark, so you always know where it's at. And they cross the 1 at pi over 4, which they have it marked right there. So again, up and down. And there we have problem 4.4. Let's take a look at 4.5. Okay, slide my paper up a bit here. 4.5 is the y equals the tangent of x, where we have negative 3 pi over 2 is less than or equal to x, which is less than or equal to 3 pi over 2. So now we're going 3 pi over 2 to 3 pi over 2. So negative 3 pi over 2 is, oh, my poor old lady eyes right here, okay? Positive 3 pi over 2 is way over here, okay? Now, these lines, these undefined lines that we set up are exactly the same. Everything we did here is exactly the same. We just have to move it over here. Now, this 3 pi over 2 is one of our undefined lines, right? So I'm going to go ahead and mark just like I did in the last one, I'm going to mark my undefined lines first. 3 pi over 2. What was this one, right? Negative, that's negative 3 pi over 2. This is negative pi over 2. Okay, then we were at pi over 2. Pi over 2, like so. And because we're going farther now, we know the next spot, because negative 3 pi over 2 was undefined. We know that 3 pi over 2 is undefined, and that's where we want to end. So we'll go ahead and mark that in as our undefined line, right? And now we just need to plot really the same points, right? In this first section here, in this first grouping, we know that it crosses the line at pi, negative pi, right? It's going to be at the, so 0, 1, negative 1, I guess mark my track. It's going to be at negative 1 when it's at negative 5 pi over 4. It's going to be at positive 1 when it's negative 3 pi over 4, which is right about here on this graph. So we go up and we go down. Okay, in the next section, it's going to be at negative 1 at negative pi over 4. It's going to be at 0 at 0, and it's going to be at positive 1 at positive pi over 4. So I went up and I went down. Okay, these graphs aren't too bad. Now this one we haven't done yet, this section, but let's take a look at what we need, right? It's going to be at negative 1 when it's at 3 pi over 4. It's going to be at 0 at pi, basically just the opposite of this, right? We got positive numbers instead. And it's going to be at 1 at 5 pi over 4. Because it just repeats over and over and over and over, okay? So go ahead and do 4.6 on your own, so you can practice doing that on your own. But I just made like a little cheat sheet, okay? I just made a little cheat sheet. Where was it at negative 1, 0, and positive 1? The 0 was just on the line. Okay, make a cheat sheet. That'd be great. I don't care. Graph it. Good job. So back to page 14, once you've finished graphing. Here at the bottom, it says, from the definitions of the sine of x being v over r and the cosine of x being r over v, we see that the function values are reciprocals. Okay, scooching up here to the top of page 15, we read that since the cosecant of x and the sine of x are reciprocals, the graph of the cosecant is more easily sketched by graphing the sine of x first. And so then they show you the values here. But basically, we've got our sine wave, right, which we did last week, last video. And the cosecant just builds off of there and makes like these bowls. Some bowls, some mounds. It just builds off of the peaks, all right? So if we plot our sine curve first, then we can plot our cosecant, okay? So the next problems here are basically graphing these cosecants. So let's turn back to our graph pages. So looking at problem 4.7, they want us to graph y equals the cosecant of x, where between negative 2 pi is less than or equal to x, which is less than or equal to 0. Again, they love to leave out the 0, but it's right here, right? 0. So I'll mark it in. So 0 as far as we're going. So we're going between negative pi over 2, or sorry, negative 2 pi to 0. Now, they've told us in the book that the cosecant is the reciprocal of the sine. So it says to graph the sine wave and go from there. So starting at, here's our 1, here's our 0, here's our negative 1, right? I'm going to work from the 0 back, and we know that at the 0 mark, we are at the 0, right? When we're talking about sine, that's where we start. And then going back, we are at the negative 1 right here at negative pi over 2. We're back up to the 0 at negative pi. We're at the 1 mark, because remember, it's a wave. It goes whoosh, whoosh, whoosh. We're at the 1 mark at negative 3 pi over 2, which is on this graph right about here. And then we're at the 0 mark at 2 pi. I think they wrote it in with like a dotted line. So I'm going to do that like this, and it comes up to here, okay? So the cosecant then wave at each one of these 0 points where we're crossing this 0 line, that is actually an undefined thing. It's a barrier for it. So we can go ahead and put our barriers in here like this, and we know where to put our bowls and our mounds, okay? Once we have our barriers in, right about here, and then here at the 0. Okay, like this. So now working off of the peaks, we basically, if the peak is at a +1, then we have a bowl. If the peak is at, or the bottom, I guess, where it bottoms out is at the -1, then we have a mound. And there we go, we graphed it, okay? So they only give us 2 of each of these, so I'm gonna do one with you, and then I'm gonna let you guys do another one on your own. So go ahead and do 4, 8 on your own, and then come back to the video. Ding, 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 ding. Well, we're gonna go ahead then and look at 4.9. 4.9 is y equals the secant of x, and we want to mark that between 0 is less than or equal to x, which is less than or equal to 2 pi. So I'm going to go ahead and 1, 0, -1. Now, the secant, if the cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine. Okay, see where we're going here? So to do this one, even though they don't give us an example in the book, and that's kind of annoying, we actually just need to plot the cosine wave and then make our mounds and our bowls from there. So looking at here, we want to go between 0, which is here, and 2 pi, which is way over here, okay? And plot our cosine. So remember, at 0, our cosine is actually up here at the 1, okay? That's where we begin. And then it comes down to the 0 mark at pi over 2. And then it goes down to the -1 mark at pi. Back up to the 0 mark at 3 pi over 2. And it is back at 1 at this 2 pi mark, right? So just like up here when we did 4.7, every time it hit the 0 mark, we had an undefined, right? Well, it's the same here when we're doing this secant. So right here, we've got an undefined spot, because this is where it crosses that 0 mark, okay, that 0 point. It also crosses here at 3 pi over 2. So those are our barriers at this point. Now I'm going to go ahead and connect my cosine dots with a wavy line, a dotted line, okay? And then I'm going to make my peaks or my bowls. I'm not going past the 0, so I only need this half a bowl here. Here I have a mound, okay? And then here I have another half bowl. So the graph is going to look like this for this one, number 9. Okay, so again, number 10 is the only other example of the secant, so I'm going to go ahead and let you do that one on your own. And I'm going to move on to number 11, which is a cotangent, which they don't show us in the book either, but it is just the reciprocal of the tangent. We're just going to flip our tangent around. So go ahead and do number 10, and then meet me back here for number 11. All right, so for number 11, it's y equals the cotangent of x between 0, which is less than or equal to x, which is less than or equal to pi. Here's my 0 right here, right? And I'm going to mark these 1, 0, -1. So I'm going between 0, I'm going to actually just mark it down here, and pi, which is right about here. That's a pretty small space, right? So the first thing we want to do is to mark our barriers. Remember how we had barriers in the tangent? Well, the barriers for our cotangent are slightly offset, okay? So everywhere in our tangent, when we did a tangent, everywhere that it crosses the 0 mark, that is the barrier for the cotangent. Now, I'm sorry that they don't get to go into this more clearly, but that's what I can tell you. So I know that on my tangent mark, for my cotangent, my first barrier that we need here is going to be at 0. Okay? And then the next barrier is the next spot in the tangent line where it crossed the 0, which is at pi. But that becomes a barrier for my cotangent. Now I'm going to go ahead and mark the rest of these cotangent barriers so that you can see them for when you do problem number 12 on your own. So my next barrier then here is going to be at negative pi. I'm going to go this way. Oops, forgot to do the bottom half. So this was at negative pi. This is at 0. This was at pi. Okay. The next one then is at 2 pi. 2 pi. If you can't have 1, have 2, right? 2 pi, negative, this is the negative 2 pi, right? Negative 2 pi. So then, of course, we're going to have a barrier over here at positive 2 pi. Okay, so that's the difference, or one of the differences, between a tangent and a cotangent. Now, the other difference between the tangent and a cotangent is the curve is opposite. So thinking back literally to a page ago where we did the tangent, the curve started down here in the negative, right? Went up to the positive. Well, for this one, from left to right, we're going positive down to negative. Okay, other than that, the points are going to be very similar, right? We're just off a step. So we're supposed to be working here between 0 and pi. So the point in the middle is where it's going to cross the 0 line, right? The point in the middle. Then it's going to go down. If we go to the right, it's going to go down, and it's going to go down to that 3 pi over 4. It's going to be at the positive 1 at the pi over 4, okay? So this one just runs kind of like a mirror image of the tangent, and off a step. You know how the sine and the cosine are almost exactly the same, except they're off a step. Well, the tangent and the cotangent's the same thing, right? It's off a step. These aren't the same barriers. So please make note, if you're making your note card of where your tangents and your sines and your all that stuff, please make note that the cotangent, their barriers, their undefined parts are slightly off from the tangent, okay? It's like one quarter cycle or 1/2 cycle off, right? But that's it. That's the setup. This is what it looks like a mirror image of the tangent. So go ahead and mark that down. Good job. Section 5 begins on page 17, and it's about applications. It says the following problems are applications usually found in the study of physics. They are direct applications to the radian measure of an angle, okay? Speed and angular velocity are the terms that are defined. So here is speed. Speed, when a body moves with a constant rate of motion, which is v in time, okay, so v represents our constant rate of motion in t for time. Okay, constant rate of motion is v, time is t. The distance, s, that the body travels is expressed by such a formula. So the distance, which is s, is represented by s equals v, okay, that constant rate, times time, right? Distance equals rate times time. It's just that they're changing it up to s equals v times t. It's kind of strange, but it's not the first time they've done this. Solving the formula for v, or your constant rate, gives us v equals s over t, right? The fraction s over t is expressed as your average speed. So looking at these examples aren't anything we've never done before. If a person runs 600 yards in 60 seconds, what is his average speed? Well, his distance divided by his speed, right, or the time, let me try to use the correct words, right? His distance divided by the time gives us 10 yards per second. You could also write it as yards per second, okay? That's what's represented. If a person's driving car takes 5 hours to travel 250 miles, what is his average speed? His distance divided by time is 50 miles per hour, all right? We're just sticking with this formula. Distance, this is the distance equals rate times time formula. They've just changed the letters, okay? So I might stumble over it a little bit, so might you. But the formula is true regardless of the path of the moving body. Okay, we've done these problems. You've done these problems in your career of mathematics for quite a while. So these basic examples should not be a big problem. Let's move on to angular velocity. So now let's talk about angular velocity. So in this figure on the right, if we let P be a point on the circle O, okay, and it moves around the circle with a constant speed, like a record player, or if you're driving a constant speed, the tire of your car, right? The distance traveled in time will be S, okay? Distance traveled in time is S. We talked about that up here with all our definitions, right? Where's my point? Okay, as the point P moves on the circle with constant speed, the radius O of P, I guess, is generating a central angle. Remember, from central angles, the size of the central angle is the size of the arc, okay? Or the distance it's moved around here, right? So if theta is generated in time, or t, then theta over time is called the angular velocity of point P, okay? So theta, the amount the arc is open, right, or the angle, over t, which is the amount of time. The term angular accounts for the directional change of the circular motion because it's not going straight, right? It's going around and around. So the length of an arc of a circle is equal to the product of the radius and the number of radians in its central angle. So the radius and the number of radians, right? It's expressed as S equals, remember S being distance, equals the radius times theta, expressed in radians. So what we've done, what we've worked on in the past. Let's turn the page. So looking at the top of page 18, we said it says dividing by t out of nowhere, but remember that S over t, which we studied a minute ago, is the average speed, right? It's the distance over time. Rate equals distance divided by time. That is what this represents, okay? So the rate is equal to the radius times theta, or the measure of the angle, divided by time. Okay, so it says ST is the average speed of P. Theta over T, this part over here, is the angular velocity of P. So they say choosing omega to represent the angular velocity of P in the equation, it becomes R times theta, radius times theta over T, or this little radius times W. So now they've changed that the W is equal to the theta over T, okay? Because the average speed is equal to the radius times the angular velocity. The W is the angular velocity, okay? It goes from this to this. Well, it's the same thing. That's what this represents, angular velocity, okay? So, and it is expressed in radians. So what does all that mean? Let's take a look at a couple of these examples here. It says find S, which, remember, is the distance. They're using different terms, but it's the distance, when the radius is 12 and theta equals pi. Well, S is the distance, and so we're taking the radius times pi, and we get our answer. It's pretty straightforward, right? S, distance equals rate times time. And the time is the angular velocity, right? So that's where we get this from, okay? So rate times theta. S equals R times theta. What about R when S is 16.4 and theta is 2/3 pi? Remember, because our theta is always going to be in radians. So this time, here's our formula, okay? But we are substituting in our S and our theta and solving for R. Nothing we can't handle, right? The strange part is I would have left the answer here like this. I'm not sure why they took it the extra step here, but didn't take the extra step here. So either way you want to leave it, if you want to leave it with your pi, or if you want to actually finish it out by dividing or multiplying by 3.14, either way is fine. So let's do a couple of these together. Down here at the bottom of the page, 5.1. S when R is 24 and theta is pi over 2. So remember, I'm going to write it right here. S equals R times theta. Okay, so S when R is 24 and theta is pi over 2. This one's pretty simple, right? 2 goes into 2 one time. It goes into 24 12 times, so it's 12 pi. I'm just leaving it at pi. Like I said, if you want to continue the problem and multiply by 3.14, that's fine. Do what you want. I'll figure it out. All right, what about S when R is 18.4 and theta is 3 pi over 4? Okay, we're going to need a calculator for this one, although 2 goes into 4 two times and it goes into 18.4, like 9.2. We can reduce a little bit, but we still need our calculator to solve. So 9.2 times 3 divided by 2 is 13.8 pi. Okay? Now we're solving for R when S is 26.4, and that's going to equal R times 3 pi over 2. So how do we move a fraction around? Well, we multiply both sides by the reciprocal, right? So it's going to be 2 over 3 pi. This is going to be multiplied by 2 over 3 pi. Okay, these cancel, and we're left with our R. So 2 times 26.4 divided by 3, we get 17.6 over pi. Okay, they left theirs over pi, so I'm leaving mine over pi. We can do one more, number 5, together. This time they want theta when R is 10 and S is 27. So S is 27, R is 10, and we're looking for theta. Well, we just divide both sides by 10, right? So our theta is going to be equal to 2.7. Okay? Pretty straightforward. Let's continue on to page 19 here. Now for page 19, they've got examples here. We're doing story problems now. We're coming out of just giving us information straight up. We're doing story problems. So let's take a look at these couple story problems and then we'll work on some together. So what is the speed in inches per minute of a point on the rim of a record 10 inches in diameter? So if our diameter is 10 inches, then our radius is 5. Turning at a rate of 45 revolutions per minute. Okay, so first we have to figure out the radians, right? 45 revolutions per minute. Remember, 1 revolution is 2 pi. Remember our circle from before? 1 revolution is 2 pi. Okay, so 2 pi radians. So they took 45 times 2 pi, gave us 90 pi radians per minute. Okay, now we have it in radians. So then it says in 1 minute, the point travels an arc with a central angle of 90 pi. 1 minute, so per minute, it goes 1 revolution, which is 90 pi radians. Therefore, in our formula, okay, the radius is 5. The W, or omega, right, the angular velocity is 90 pi. Okay, so we take 5 times 90 pi and we get 450 pi. I assume they multiplied it by 3.14. Let me see. Yes, they did, to get 1,413 inches per minute. Now this, I understand multiplying it by 3.14 because you're trying to get a complete answer of how fast it's going around, right? So, or how far it's moving. It's moving 1,413 inches per minute. Okay, it's a lot. Number 2, a flywheel makes 120 revolutions per minute. Okay, what is the angular velocity in radians? So remember, our angular velocity is theta over time, and our theta is the 120 revolutions per minute. They're just writing it a little bit different, right? So 120 revolutions per minute, per 1 minute, and a revolution is 2 pi. So 120 times 2 pi tells us it's moving 240 pi radians per minute, basically. Okay, so this is what we're doing, story problems. Not that much different than these little problems at the bottom, just they're at story problems now, and so we're going to have to work it out a little bit. So, number 7. A wheel turns through 20 revolutions per minute. Find its angular velocity. Well, 20 revolutions per minute, it's still 2 pi, right? A full revolution is 2 pi. So that's going to be 40 pi radians. So I'm going to write it as RAD. Okay? Sorry, radians per minute. We want to make sure we put our unit of measures correctly. Number 8, a wheel turns 200 revolutions per minute. How fast does it turn in radians per second? Okay, so now we have to do a little bit of conversions, right? So we've got 200 revolutions per minute. So that's our 200 times 2 pi. So this is per minute, right? So what is our conversion? Well, 1 minute is 60 seconds, right? So here my minutes can cancel. That's our conversion. So now we have to figure out 200 times 2 pi, which is basically 400 pi, right? Divided by 60 seconds. We can get rid of these zeros and then grab our calculator. So I took 40 divided by 6 times 3.14 because we want without the pi this time. And I got 20.9 rounding because it was 0.93333 radians per second. Okay, that's where we've ended up. 20.9 radians per second. All right, good job. Now, if you didn't multiply out the 3.14 on that one, I wouldn't mark it wrong. Okay. I know that it's not clear when we should or where we shouldn't, so, you know, it's okay. I'll be able to figure it out, your answers. All right, so a circular gear turns at 60 degrees per hour. Through, how many radians does it turn in a 24-hour day? Well, first we need to figure out the radians here, right? So 60 degrees times pi radians over 180 will tell us how much we got here, right? So how many times does 60 go into, or let's see, 6 go into 18? So it's going to be 1 pi radians over 3, right? So basically pi over 3 radians. Remember, we did this back in book 3, I believe on page 33 of book 3, has the formula to go from degrees to radians and radians to degrees. If you don't remember, make sure you go back and check that, okay? So, through how many radians does it turn in a 24-hour day? Well, it's turning this much each hour. So, to find a 24-hour day, we would take pi over 3 times 24, right? That's pretty straightforward. 3 goes into 3 once, it goes into 24 8 times, so 8 pi radians per day. Okay? 8 pi radians per day. Let's jump down and do one a little bit further down. I want to do number 13 next, and I got to grab a scratch piece of paper because there's not a lot of room on this one. So number 13 reads, oh, and I've totally, there we go. That was weird. Number 13 reads, as the minute hand of a large clock forms an angle of 52 degrees, the end of the minute hand traverses a distance of 23.5 inches. Find the length of the minute hand. So we're looking for the radius technically, right? So first we have to change our 52 degrees over to radians. So 52 degrees times pi radians over 180, okay? So what is that going to be? Something messy, but let's take a look here. Probably nothing clean. All right, so 4 goes into 52 13 times, and it goes into 180 45 times. It's probably about as clean as we're going to get it, and I'm going to leave it like this for now. 13 pi over 45, okay? I'm going to leave it like that for now. But remember our formula over here, right? So the 23.5 is going to be equal to our radius, which we don't know, times 13 pi over 45. So now we have to multiply both sides by the reciprocal. So 45 over 13 pi. 45 over 13 pi. And then we will have our radius, right? So 45 times 23 is 1057.5 divided by 13 pi. I can't imagine 13 goes evenly, but let me check real quick. Well, it doesn't go in evenly, but it would be 81.3 over pi. Now, if you wanted to finish it off, because we're talking about a radius, we're talking about a distance, so we probably should divide by that 3.14. Let's take a look. And that would be 25.9 inches, because that is our unit of measure, okay? So 25.9 inches. Now, if you are doing this work on a scratch piece of paper like I did, please include that when you turn in your self-tests so that I can check your work, right? I need to be able to see what you're doing. So, story problems. Same basic setup. You just got to make sure you're pulling out the right information. Revolutions per minute, make sure you're turning them to radians before you start doing your work, right? So like we did with this degrees here for number 13. 52 degrees was how many radians, right? That was their first step in solving that problem, all right? That is section 5. Good job. Lesson 6 begins on page 21, and it's the amplitude of circular functions, okay? So the amplitude of trigonometric function is the maximum displacement on the graph of that function, okay? So that's this, right? How far does it go from the top to the bottom? So in the case of this sine function, it's 1, right? Its top goes to 1, its bottom goes to -1. So if you have y equals the sine of x, there's an a, there is a coefficient right here. In this case, it's just 1. So the amplitude is to the absolute value of a, or the absolute value of 1, which is 1. All right. So the amplitude of this basic sine wave is 1, which makes sense, right? So that determines the height. But it says here for the amplitude for the tangent, cotangent, secant, and cosecant, right? Because they look a lot different. It's infinitely large regardless of the a. However, for a limited domain, the value of a would determine the maximum height of those functions. So tangent, cotangent, secant, and cosecant have a different setup, right? We already know that because their graphs look different. But we're talking about sine and cosine. So if we look down here, here is the basic chart, right? We've looked at this chart several times. Here is the different points, right, for the sine of x. And so if they change it to the 2 sine of x, then everything is multiplied by 2, right? 1/2 times 2 is 1. Here we have the square root of 2 over 2. Everything here is multiplied by 2. It just grows, okay? So the square root of 2 over 2 times 2 is just the square root of 2. So forth and so forth. 1 times 2 is 2, right? So then here they have the picture of it. So now we have a higher amplitude, right? This is radio waves and ultrasound technology. That's all that type of stuff is what they use this information for, okay? Let's turn the page. So basically the graph is exactly the same, except the range, if you multiply it by 2, right, is going to be different. So it's -2 is less than or equal to g of x, which is less than or equal to 2, right? So 2, the cosine of f of x is 2 times the cosine of x. The wave is basically the same, except now we're going to -2 and +2 as our highs and lows, right? We're still crossing the 0 line at the same points, okay? We're still marking our -2s and our +2s at the same spots that we would mark our 1, right? It's just our range is different. So then if we look at the tangent, so here's a y equals the tangent of x, and here's a y equals 2 times the tangent of x. Not much different, right? This one might be a little bit more narrow. Not a whole lot of difference, okay? So let's do a couple of these graphs. I'm going to graph them on the graph paper in this book. So I'm going to write down the problems, and then we'll flip over to some random graph paper page back there, okay? All right, so I'm just back here in the back of the book, and we're going to do number 6.1, which is y is equal to 3 sine of x. So remember, this is our 0, and this dotted line represents our 1. And just to keep it, I don't know, even, the 1 is technically 2 check marks away or 2 blocks away. So then block, that's a 2 block, and here's our 3, right? So we have to, I'm just keeping it consistent. So skip 1, that's a 2, skip 1, that's a -3. Okay, this is my -1. All right, so we are graphing y equals 3 times the sine of x. Now, we know, here's my other 0 mark. Right, we can mark it right here, I guess. We know that at the point 0, 0, sine is 0, right? That's where our sine starts. And then it goes on from there. So at pi over 2, which is right here, which is basically 90 degrees, right? Our regular sine graph would be at 1. Well, we're not doing a regular sine graph, right? We're doing it 3x, or 3 times sine. So instead of being at 1, it's going to be way up here at 3. And then we know that at pi, it's back at 0. Okay, 3 times 0 is 0, so that doesn't matter. And then when it gets to 3 pi over 2, which is right here, we know that it's going to be down here at -3, okay? And then when it's at 2 pi, it's back at 0. One circular motion of this is fine. You want to fill your graph paper because you're feeling adventurous, go for it. Okay, but there it is. There's our representation of 3 times sine of x. Now let's look at 6.2. 6.2 is y equals 1/2 the sine of x. All right, so same basic principle here, right? Here's our 0, and here's our 1 and our -1, but now we've got 1/2 and a -1/2. Okay, good thing we left those extra check marks. But we're starting at the same point. We're starting at our 0, 0, except now at our pi over 2, we're only going up 1/2. Okay, at our pi, we're still at 0. At our 3 pi over 2, we're only moving down 1/2. And at our 2 pi, we're still at 0. So this one is just way more shallow, right? Okay, there's that one for number 6.2. Let's do up here. I know I'm moving my page around. Sorry, I hope I'm not making you nauseous. 6.3 is y equals 1/3 the cosine of x. All right, a third. Ugh. All right. Here's my 0 mark. I am actually going to change this up here to be my 1. 1, 2, 3 pieces away. 1, 2, 3 pieces away is my -2 is my -1. This way, each block is 1/3, right? I know it has a dotted line. I don't care. But here's the thing we need to remember for cosine, right? Cosine doesn't start at 0. At the 0, where's my cosine? It's at 1, right? Well, but now I'm doing a third of that. So instead of being at 1, it's going to be at a third, which is here. Okay? Then at pi over 2, it's at 0. At pi, it's going to be the 1/3. At 3 pi over 2, it's back at 0. And then at 2 pi, we have the 1/3. Okay? So, boom. There we go. All right, I want to do one more with you guys. These aren't too bad, and that's going to be number 6. So 6.6 is f of x is equal to the -1 times the sine of x. So don't let this freak you out, okay? But let's take a look here at, here's our 0. I like to get this all set up. 1, here's my -1, and then here's my 0 point, right? We're starting at the 0 point regardless, because 0 times -1 is 0. But what would be my next step? My pi over 2 is 1, but I need to multiply that by a -1. -1 times 1 is a -1. So this time it's going to be down here, okay? My pi is still 0. 0 times -1 is 0. 3 pi over 2, I would be at a -1, but a negative on a normal sign, right? But -1 times -1 gives me a +1. So now I'm up here. And then at 2 pi, I'm back at 0. So that's basically it. For each value of your sine or cosine, you basically are just multiplying it by this, okay? And so this time my sine wave is like opposite of the normal. But we still recognize it as a sine wave because it's at the 0, 0. We know that that is what a sine wave looks like, okay? So that's the graphing portion of this. I'm going to throw back now to the lesson because there's a couple of problems at the top I want to look at with you real quick, and then we'll be done with this video. So here at the top of page 23, it asks us for amplitude and range of a couple of things. Now remember, the amplitude is the absolute value of A. So, and A is this coefficient right here. So the amplitude of y equals 2/3 sine of x is 2/3. Okay, these aren't too. I don't want you to feel like, oh, they're asking me something hard and I'm not getting it, when they're really asking you something pretty simple. The amplitude of y equals -3 sine of x. So -3, but what's the absolute value of that is 3. The amplitude then is 3. Okay. Oh, my goodness gracious. 3. Now, the range of f of x equals 5 sine of x. What is its range? Well, it's going to be -5 is less than or equal to f of x, right? Which is less than or equal to 5. Okay, the range is represented here as well as the amplitude, right? When we multiplied it by 2, the range was either +2 or -2. It was everything, it was in between those 2 points. Well, this time it's multiplied by 5, so that becomes our range. Okay, I just wanted to go over those a little bit with you. So that's it for this lesson. As always, if you have any questions, please let me know via text, or you can reach me in my office hours. Otherwise, until next time.